Welcome back, everybody. So today we have a really important topic: understanding, presenting, and interpreting statistical results. This is an area where you can really make a difference. You're sitting in your office, somebody walks in, you know they're studying an incredibly important topic. They're trying to predict the next war. They're trying to predict the next pandemic. They're trying to explain what causes mortality rates. And they look at the results and they say to you with some excitement, I have 2 asterisks, or it's significant. Really, does that matter at all? If they had not taken a statistics course, but they had substantively important results, would they have described it that way? If they're really trying to talk to people who understand these problems, would they be saying things in lingo that only methodologists think they understand and actually they don't really understand? It should be the case that we understand for ourselves, present and interpret statistical results for others in ways that they understand. And that's what we're going to work on today. So let's get started. Here we go. All right. So in order to figure out how to present statistical results, let's start with how not to present statistical results. Here's a graph which comes from some article that I don't really want to know where it comes from. I never actually knew where it came from. That's not important. But I want you to look at this result, and I want you to tell me if it has meaning for you. Let's remember that when you write an academic article, the rule is that your tables and your figures should stand independently. What that means is you should be able to read them, understand what's in them without reading the text. And of course, you should be able to read the text that describes the figures without looking at the figures, and you should also understand them. That's sort of a rule of how you write academic articles. So let's look at this table and figure out whether we have any idea what's going on. And I think basically the answer is no. So the table 1 is predicting which ethnic group conquered most of Bosnia. The dependent variable, I assume, is which ethnic group conquered most of Bosnia. But what's the dependent variable exactly? It's which ethnic group? No, presumably it's one of the ethnic groups rather than another one. Maybe it's binary or maybe it's not. But, well, presumably it is binary because over at the bottom here it says unstandardized coefficients for logistic regression. So I don't know why they were unstandardized to begin with, but it says logistic regression. So it must be that the dependent variable is binary. So it says that the title is predicting which ethnic group conquered most of Bosnia. So which is the 1 and which is the 0? I don't know. Let's look at the numbers in this table. What do they actually mean to you? So attention to Bosnia crisis. You don't know whether the 1 or the 0 refers to any particular ethnic group. And then you got a 0.609. Does that mean something different than if it was 0.608? If there's 2 asterisks there, which at the bottom says P less than or equal to 0.012 TALD, what does that mean to you? Okay. Does that convey something about the Bosnia crisis? Which ethnic group conquered most of Bosnia is presumably this must be a survey, and it must be whether it's knowledge of these things. But does it convey that to you? We can look down and we can see some interesting things like constant. Constant is something that has a number. Oh, great. And how about number? Here, look, that's a number. Apparently, none of the other things in this table in this right column are actually numbers because only this one is labeled number. Oh, and here's the minus twice the log likelihood, right? So now remember we explained earlier that log likelihood is not relative, is only interpretable relative to other models run on the same data. So if you only have one likelihood, you only know the height of the likelihood surface for one value, in this case presumably the maximum likelihood value. You know the height of it, but they're not telling you the height of it relative to any other value. So what meaning is that? I don't know. But fortunately they have the goodness of fit right under it. No indication of what goodness of fit statistic it is, I don't know. Then they have these 2 R-squared things here, Cox and Snell and Nager-Knagel, which frankly, I haven't the slightest idea what they are. I haven't heard of them before or after this article. I'm sure they have some important heritage, but I don't know why they're here. If they're here, there should be a reason why they're here. This log likelihood, by the way, is 7,215.2 231. If there's a number, a numeral, if there's a numeral in your table, it had better have some meaning such that if it were changed, it would matter. So if this were 7215.232, would that matter? I mean, at all? At all? Okay, so if this were 609 instead of if instead it were 0.6, let's suppose, I mean, I don't know whether it matters, okay? But if most of the numerals in this table could be swapped for other numerals and it doesn't change the meaning, then you're presenting a table full of numbers that don't actually have any content. Another thing is just the way that you present it. Let's suppose these have more meaning. Presumably in the text of this article, they explain some more than we could extract from this table. But why so much white space? Like, is this number connected to where? Which one of these? It's not entirely, I mean, obviously you could put your hand on the piece of paper or a ruler and try to figure it out. But you're trying to make it easy for people. This doesn't make it easy for people. The stars, we call it stargazing. It's not entirely clear what it means, what hypothesis test you're testing. Why in this context you're making a decision rather than trying to estimate a quantity, some kind of quantity of interest. Can any of these be estimated, any of these estimates be interpreted as causal quantities? I don't know. In order for them to be causal quantities, as we will all see later, they need to be in here as exogenous, so they can't be affected by the outcome variable. They have to have no post-treatment bias, and so all the other variables must be causally prior to it. It's not clear that any of these things were considered here. Can you compute a quantity of interest from these numbers? So in other words, let's suppose these are just logit coefficients, which they appear to be, and you wanted to calculate a quantity of interest from them. Well, to simulate, as you saw earlier, you're going to need the variance-covariance matrix. So you're not getting the variance-covariance matrix. You're not even getting the standard errors. So how are you going to simulate any quantities of interest from this? It doesn't seem like you can. This is not a good representation of how to present statistical results, but it's not rare, and I think we should all aim to make it more rare. Once you make your results crystal clear, it actually changes the entire analysis. People often will write their paper before they're really clear on what their results are. I think that's a real mistake because you don't really know what your results are until you've figured out exactly what the quantity is that you're estimating and then what the estimate is. And once you see it, that can change how you're describing and presenting your whole analysis. So this is how not to present some statistical results. So let's try to figure out how to present them in a somewhat better way. All right, first of all, what are the goals? What are the goals of interpretation and presentation? Statistical presentations should do four things. They should convey precise estimates of the quantity of interest, and there should be a quantity of interest that you can identify that others really have an interest in. Second is they must include measures of uncertainty, not only a point estimate, but every point estimate must come with a measure of uncertainty. There should be little specialized knowledge that's required to understand the estimate of the quantity of interest. That's a really important step because remember, we're in this for the substance, not for the methods. And so it should be the case that the methods help you see clearer. It can't be the case that we make snide remarks at people who can't read our work because it's too technical for them and they didn't have the right statistics classes. We're writing for them, right? We're not trying to make them into methodologists. We're trying to understand the substance and make a contribution to the substance. To do that, our results, our final results, should require little specialized knowledge to understand them. Of course, it requires enormous specialized methodological knowledge to know whether the analysis is right and to do the analysis and to figure out whether you've made all the corrections you should make and whether it's possible to do any better, etc. But when you're presenting and interpreting and understanding the final results, they should be crystal clear to somebody who has not taken this class. And finally, we should exclude all the superfluous information that makes methodologists happy or not happy or whatever it is. There shouldn't be long lists of coefficients that don't have any particular meaning. There shouldn't be any stargazing. There shouldn't be silly summary statistics. There shouldn't be too many decimal points. Every number that you present as a final interpretation for substantive people should be understandable. It should not be the case that you come in with a paper to my office, if we actually have offices again, and look at, and you and I look at the results and we find a number in there, and I say, hey, what does that number mean? And you say, I don't know, but it's significant. You don't ever want to be in that position. I don't mean with me, but you don't want to be in that position. You want to be presenting results that have crystal clear meanings. Okay, so all of our methods of interpretation and presentation should have these 4 parts. So for example, we should be able to utter sentences like the following. Other things being equal, an additional year of education would increase your annual income by about $1,500 on average, plus or minus about $500. Okay, we could be more precise than that, but I think that gives you a pretty clear and intuitive and substantively meaningful way of expressing a set of statistical results. Okay, so you want to try to satisfy somebody who understands the methods or thinks he does, like me, and somebody who tries not to pay any attention to the methods but are pretty smart, like my folks or your folks. This is the article that I wrote that led to this lecture. In fact, this is the article that I wrote that came out of this lecture. Okay, and it was, by the way, it was with Mike Tomz, who's a professor at Stanford, and Jason Wittenberg, who's a professor at Berkeley, and both were in this class previously. So what we're going to do is we're going to simulate quantities of interest, and that's how we're going to focus on this. So what do quantity of interest simulations get us? They get us complete flexibility. They get us the ability to express our quantity in any format that we wish, in any format that is compelling to our readers, along with uncertainty estimates. That's what they give us, flexibility. They summarize everything we know and everything we don't know about a quantity of interest given the model. They give us complete flexibility of presentation and a great test of whether we understand the model. Because if we can't simulate from the model, then we probably don't understand the model. But if we can, then that's a good way of us figuring out that we really understand the model. Our goal is to simulate quantities of interest from the model, so now we have to figure out how to do it. Here's the model. First part of it is the stochastic component. So we have y of I is distributed in some way. I sometimes write this as p, sometimes as f. That's our distribution given theta and alpha. Theta is the parameter that is in the systematic component. So this is these two equations form the general way that we're going to express statistical models. So how do we simulate quantities of interest from this setup? That's really our question. And first thing we're going to do is do estimation uncertainty, and secondly, we're going to do fundamental uncertainty. So those are the two pieces that we have to focus on. So we're going to get estimation uncertainty first. Why is that? Well, if you look at the two equations there, there's really only two things that are not known. Because you remember, f and g and x are all specified ahead of time. F and g and x. Theta is just a function of everything on the right-hand side of the systematic component. So that we totally know. And y gets drawn from the model. So the things we don't understand, the things we don't know ahead of time, are alpha and beta. Those are the two things. So those are the things we need to estimate. And we're uncertain about them, and therefore we have estimation uncertainty. We have estimation uncertainty because of the I like to say because of your inadequacies, because of our inadequacies, right? Because of our research design. We didn't have all the resources to collect all the data in the universe. And because of that, when we're estimating alpha and beta, there will be some uncertainty left, and it's our responsibility to reflect that. So the first step in simulating quantities of interest is to simulate alpha and beta, and to have those simulations reflect all of our uncertainty. Then we're going to just simulate y, because we sort of know everything we know at that point, right? Once we've simulated alpha and beta to reflect our uncertainties, and given the data, we know everything else, and so we just need to draw from the model. So then we simulate y, given the simulations of alpha and beta. which represents the fundamental uncertainty, as it says here, due to the nature of nature, which is always uncertain. Finally, we'll have simulations of y, and from that we can calculate any quantity that we deem to be of interest. Okay, so that's going to be the whole setup. It's just those 3 steps. So first step is how we simulate the parameters. So the goal is random draws of the parameters from a sampling distribution. Other words for a sampling distribution or a posterior under Bayesian analysis with a flat prior. Okay, so same thing. How to do this is we're going to maximize the likelihood with respect to all the parameters, alpha and beta, which I'm going to just vec, which means stack them up, and put them in one Greek letter so that we only have to talk about one Greek letter rather than 2. So we're going to stack them up and call them gamma. Okay, so we maximize the likelihood function once. We don't have to keep doing that because we're only going to get one number unless we had more than one data set. And although we imagine there are more than one data set to get the sampling distribution, we only get to observe one. So we maximize the likelihood function one time. Second, we will record gamma hat, that's our maximum likelihood estimates, and the variance of gamma hat, which is the variance covariance matrix or the variance matrix or the covariance matrix, which if there's k elements in gamma, this is going to be a k by k matrix. The diagonal elements are the squares of the standard errors. Okay. Then we're going to draw gamma hat from which we're going to draw gamma from the multivariate normal. We're going to call it gamma tilde in order to reflect that it's simulated. And we're going to draw that from a multivariate normal distribution. Why is it a multivariate normal distribution? Ask that of yourself. Pause just for a second. It's a multivariate normal distribution because of the central limit theorem. Okay, it's not the multivariate normal distribution because the stochastic component is normal. It does not need to be normal. We're still going to use the multivariate normal here to reflect estimation uncertainty. So the central limit theorem enables us to do that. That's an approximation, depends upon large enough samples or a model that's close enough to a normal model. But we're just going to do this for now, and we're going to draw many simulations of the parameters from the normal model, given the maximum likelihood estimates as the mean and the variance covariance matrix as the uncertainty. They came from here, right? So it's direct. This move here reflects all of the uncertainty in the estimated parameters. If we knew the estimated parameters exactly, then this variance would be 0, and when we drew the simulated parameters, they would always be exactly the same. But of course, it's never going to be exactly 0. And so when we draw the simulated parameters, they're going to vary. The parameters that vary the most are the ones we know the least about. So they reflect the uncertainty and the type of uncertainty, and they reflect all the knowledge we have about those parameters. Okay, so when we simulate, there's 2 things that we could think to simulate. We could simulate expected values, and we could simulate predicted values. So let's just take a little detour and think about those 2 things and explain how to simulate expected values and how to simulate predicted values, since they will be either our quantities of interest or they'll be useful on the way to our quantities of interest. Okay, so definitions of what these things are. So predicted values are draws of y that could in principle be observed, like the election outcome. Expected values are draws of features of the distribution, right? That maybe the distribution of election outcomes, and a feature might be the expected outcome of the election, the variance of the outcome of the election, the probability that a candidate will have more than 50% of the vote. So that's the difference between predicted outcomes, which are observed, and expected outcomes, which are features of the distribution, often means and things like that. The sources of variability in predicted outcomes should always be estimation and fundamental uncertainty, including simulation the way I just described. In expected values, the only source of uncertainty is estimation uncertainty, because they sort of came first in the whole algorithm, right? Alpha and beta, when I showed you the two equations again, that's the first step of simulating y. So if you're only interested in that step, You just have that step. It's the only uncertainty is the estimation uncertainty. You can, of course, go all the way to the predicted values and calculate other features, other representations of the expected features of the distribution. Okay. So as n goes to infinity, does the variance go to 0? Well, what goes to 0? For the predicted values, no, it doesn't, because there's fundamental uncertainty, right? And even though for the expected values, as n goes to infinity, our inadequacies basically are going away, and therefore we presumably get an exact estimate of the alpha and beta parameters that we would like to estimate. And so we know those exactly, but then the expected values go into the model, and we simulate the predicted values, and those have fundamental uncertainty. Even if we collected a large sample, that doesn't constrain the world from its usual process of producing uncertain results. And so as n goes to infinity, the variance of predicted values don't go to 0. So an example is for temperature. We might be interested in whether the temperature is less than 32 degrees, whether it's freezing. And there's different ways of asking the question. One is for predicted values, we might just ask the simple question, what's the probability that the temperature is freezing tomorrow? What's the probability that the roads will freeze tomorrow, that the temperature is less than 32 degrees tomorrow? So we could calculate that. But we might also be interested in the expected value. What's the probability that the average temperature, right, on average for all the years like this one or something like that, is less than 32 degrees tomorrow? In this little graph, the blue one is the predicted values. The piece to the left of 32 degrees is freezing, and that's a very straightforward case of just asking what the predicted value is. The distribution of the expected values is we're only interested in the expected value of that predicted value distribution. And in this case, the expected value is just the mean. We could be interested in other features like the variance or things like that. But our knowledge of the mean of that distribution is of course greater, and therefore the variance is less. And so you could see the red area to the left of 32 degrees is smaller than the blue area to the left of 32 degrees. Okay. So let's talk about simulating predicted values, then we could talk about simulating expected values. Predicted values can be for forecasts about the future. They can be about farcasts, as I call them, which is for some area, perhaps some country for which you don't have data. So you can make a farcast for that, which is sort of like a forecast. It's not really fundamentally different than a forecast, except for the fact that you know that it actually exists, and we don't really know for sure that the future is going to even exist. But with that technical aside, they're essentially the same thing. You can also think about nowcasts, which is about the current data, where you might like to take the model and reproduce the data that we have to see whether the model fits. You can also do counterfactual forecasts. What would have happened if we change one of the x's to a value that it does not actually have now? And that would be a slight deviation from a nowcast. So to simulate predicted values, we repeat once for each random draw of y tilde, tilde meaning that it's simulated. We draw one value of gamma tilde, so those are our parameters, the only parameters of the model, alpha and beta. Where do we get them from? We get them from a normal distribution due to the central limit theorem. It's a multivariate normal distribution. It has mean equal to the maximum likelihood estimates, and it has variance equal to the variance-covariance matrix that also gets estimated when we calculate the maximum likelihood estimates. Second, we define a vector of values of the explanatory variables. Since we're going to choose it, I'm going to call it x sub c for choose, which defines the predicted value to compute. Right? If you're going to have a predicted value, it has to be a predicted value of something, and we're going to define what that something is based upon x sub c. We're going to extract the simulated beta from gamma, right? Because gamma is the vector of beta and alpha stacked on top of one another. So we're going to just pull off the betas. We're going to stick them into this function g. So we have g of x of beta tilde. If that's a logit, it's 1 over 1 plus e to the minus x sub c beta tilde. And if it's linear, it's x sub c times beta tilde, etc. So now we have simulations of theta tilde C. Then we simulate the outcome variable by taking the simulated theta C and alpha and sticking them into the stochastic component and taking a random draw of y of C from that. We don't stick beta in there because beta is already doing its work through theta. Okay, so what can we do with lots of simulations of y? Like, how would you present that? Well, there's lots of interesting things we could do with that, right? For one choice of a set of C values, like the values of those variables in predicting the 2020 election, we could do the things with it that we talked about a couple of lectures ago. We could present a histogram of those values. We could take the mean of them. We could be particularly worried if they get larger than some value, so we could calculate the fraction of them that are larger than that value. There's a lot of things we could do with these. So a histogram, an average, a variance, percentile values, all kinds of things. You should choose those based upon what is compelling or to you and what is likely to be compelling to your readers. Okay, so that's predicted values. Now let's talk about simulating expected values. Okay, so how are we going to simulate expected values? Here's an algorithm. We're going to draw one simulated expected value as follows. Draw one value, that is, simulate one value of gamma tilde, which is, again, vec of beta and alpha, which gives us the estimation uncertainty. You know how to do that, by the way. How do you do that? Well, you get those from their multivariate normal distribution with parameters that you got from the maximum likelihood estimates. We're going to choose one value for each of the explanatory variables. So again, we have x of c, which is a vector. We're going to compute theta c tilde by sticking it into the systematic component, which is g of xc of beta tilde, given one simulated value of beta tilde and from gamma tilde. So again, we pull out just the betas to use in that systematic component. Then we draw m simulations, where m is a sufficiently large number, of the outcome y sub c. But since there's m of them, I'm going to have a superscript to explain which one of the m we're talking about. So I'm going to call it k. So that's what the superscript of k is. And this will simulate the fundamental uncertainty from the stochastic component. So remember, we have m of these. Now we're going to average over those m. We average over the fundamental uncertainty, average over the m simulations, which give us one simulated expected value. Remember, the expected value is just an average, so the idea that we're going to get the average by taking the average makes a lot of sense. Okay. Now, what do? Well, we repeat this entire algorithm, capital M times different than little m, which gives us, leaves us with estimation uncertainty. Finally, we have these m things, these m estimates, from which we can calculate our quantities of interest in the way and the format that we choose: histograms, averages, point estimates, standard errors, confidence intervals, etc. So interpretation. When little m is 1, you get the same value as the predicted values. So without that little inner loop, D and E, then we're going to get predicted values. With a really large m, the reason why m should be larger than 1 is that you get better fundamental uncertainty approximations. When the expected value of yc is equal to theta c, right, in that special case when those are actually the same thing, we could skip steps D and E exactly. So for example, in the logit model, once we, in this step here, this is a pi in the logit model, and this is 1 over 1 plus e to the minus x beta. In that case, we have simulations of pi. We could go another step, which is not necessary, but we could go to step D and E by simulating y, which is a bunch of zeros and ones, from the model with this is pi. Where would we get the zeros and ones? From the Bernoulli distribution. But if we simulated the zeros and ones, and then in step E took their average, we would get back to pi here. So there isn't really any point in doing D and E in the, because these two things are the same. So sometimes you can skip those. But just to be clear, you don't ever have to skip them. You can just take steps A, B, C, D, and E and always apply them no matter what, and then you never need to think about this at all. So until you're comfortable, just do them all. Once you're doing them all, if you're doing a case like the logit, and you're at some point in the code, you'll realize, wait a second, I have pi, or my estimate of pi. Now I'm going to, and pi is like 0.7, and now I'm going to draw zeros and ones from a Bernoulli with pi equal 0.7. And that means 70% of the draws approximately will be ones, and 30% will be zeros. And so now I'm going to take an average. What am I going to get? I'm going to get 70%. So why did I do that last step? I'm going to skip that last step next time. That's good thinking, okay? But if it's confusing at all, don't do it, because it's not necessary, okay? Just go through and, that is, don't skip the step. Just include the step until you're comfortable, okay? All right, so let's talk. We've now talked about simulating expected values and simulating predicted values. So let's talk about another quantity of interest that we looked at a simple version of earlier using predicted values. Using plugged-in predicted values with beta hats and stuff like that. But now let's do it the proper way and simulate first differences instead of doing it the other way. So we're going to simulate first differences. So one draw. So to draw one simulated first difference involves the following. We're going to choose vectors of x sub s for the starting point and x sub e for the ending point. Works just like before. We have to choose those. Maybe they're all the same except for the value of one variable. Maybe the s is for New York and the e is for Chicago, and we're going to move from the average of one to the average of the other. We get to choose what it is we wish these to be. Then we apply the expected value algorithm twice, once for the starting point, once for the ending point. And then you take the difference between the two estimated expected values. You just take the difference. And you repeat that m times so you can get uncertainty, estimation uncertainty, and reflect it. So what quantity of interest do we want here? Well, we can choose it any way we want. We could take the average of them, and that's our best guess of the first difference. We could plot a histogram of the first differences. We could plot the mean, which is our best guess, and a 95% confidence interval around that, which would be the 5%, or the 90% would be 90% confidence interval would be the 5%, and 95% percentile values of the histogram. To save computation time and to improve the approximation, we don't have to simulate beta twice, because we can simulate it once and stick it into both calculations of the expected value. Again, don't worry about it if this is too complicated. Just simulate it twice. But once you realize that you can just save a little time, you just simulate it once. Okay. So let me give you some tricks, because simulating parameters is something we're going to do all the time. So it's good to think about when we might be able to improve things. All right. So first of all, always simulate all parameters together. Always. Even though in a regression, for example, you only care about the betas and you often have only secondary interest in sigma squared, don't make the mistake of just simulating the betas. Put them all together. There are special cases, including actually regression, when you can simulate them separately, but these are rare. Almost always you'll make a mistake if you do it. You can't make a mistake if you simulate them all together, even if it's not necessary. So simulate all the parameters together. That is everything stacked up, vect in gamma. And that includes all the ancillary parameters, unless you're absolutely sure that they really are orthogonal. We're going to reparameterize to an unbounded scale, as we've done before. The advantages are that gamma hat converges more quickly in n as n increases to a multivariate normal. So that assumption that we're making that the central limit theorem applies is actually a better assumption. The maximum likelihood estimates don't change, even though you reparameterize. But the posteriors and the standard errors do, but that's actually good because they become more and more normal. So your claims about uncertainty are actually better reflective of what the uncertainty really is. It also tends to make the maximization algorithm work faster without constraints, because as I've also mentioned before, most of these algorithms either only work with unbounded parameter spaces, in which case you have to keep checking to see whether it's guessing a value outside of the feasible space and just whack it back in before it ends up dividing by 0 or something, or it can actually do it, but it doesn't do it very well. All optimization, or most optimization procedures actually work better if they use an unbounded space. It's just that's what they developed the theory for, and so that's what it tends to work for. So when we reparameterize, we actually make it easier for them as well. How do we reparameterize? Let me generalize a little bit the rules, the examples I've given you before. Sigma squared, we can reparameterize as e to the eta. So sigma squared always has to be greater than 0. Eta, if you reparameterize it this way, can be anything, and after you exponentiate it, sigma squared will always be greater than 0. So whenever you see sigma squared in your log likelihood function, replace it with e to the eta. For a probability, pi, it's not only greater than 0, it also has to be less than 1. So we could use the logit transformation, and we could say pi is equal to 1 over 1 plus e to the minus eta. That's the same notation as parentheses 1 plus e to the minus eta, close parentheses, to the minus 1, which just means 1 over. This is just another use of the logit transformation. This eta in this line means something different than the eta in this line, so I'm just reusing that symbol, no big deal. But whatever eta is in this last line, it goes through the logit transformation, and what comes out on the other side is always a number between 0 and 1. And so if your likelihood function has a pi in there, you could just replace it with this, and the optimization procedure will work better. Suppose your log likelihood function has a parameter like rho in it, which can only be between -1 and +1. Well, you can't use any of the 2 previous parameterizations, so we have to come up with another one. Turns out there's something called Fisher's Z transformation. Yeah, it's the same Fisher, same guy, same R.A. Fisher. This is the parameterization, so you could set rho equal to e to the 2 eta minus 1 over e to the 2 eta plus 1, and now no matter what eta is, it maps into the space of -1 to 1. And so these are 3 parameterizations. You may come up with another parameter that has a different type of bounded space, and so you'll have to find some transformation that fits for that. In each case, eta is unbounded. You estimate it. We simulate from it. So the assumption is that eta is multivariate normal, which, as you can see, is a better assumption than, for example, sigma squared being multivariate normal, because multivariate normal is unbounded. It doesn't make sense to say that sigma squared is multivariate normal when it can't ever be below 0, but the multivariate normal can, obviously. And then when you're done, after you've simulated it, you just run it back through this function, reparameterize it or unreparameterize it back to the scale that you care about, and is in your log likelihood function. Okay. So some tricks for simulating these quantities of interest. Let's give you some other things. We're going to compute quantities of interest from simulations of y every time, unless you're sure, which is an analogy of what I said earlier. In other words, you could stop at pi in the logit model, or you can go all the way to y. We're going to simulate simulating functions of y is also very important, because lots of times, for example, we may be analyzing income as a dependent variable, and it's very common to take the log of that. So in analyzing the log of y, the right way to do it is you simulate, if log of y is your dependent variable, simulate the log of y, and then you get to apply the inverse function and take the exponentiation of the log of the simulated y to reveal the simulated. So you could simulate y, and you can do it this way. Right? You could simulate the log of y. You get a simulated value of this, and then just exponentiate the simulated value of this, and you get back y. With simulation, you can do the intuitive, easy, obvious thing. But don't do it without simulation, because it's actually wrong. So the wrong way, but still the apparently intuitive way, but the wrong way, so don't do this, okay, is regress the log of y on x, right? Compute the predicted value before you do simulation, right? You just plug in the plug in the y-hats. Compute the predicted value of log y hat, and exponentiate that thing. That's wrong. Why is it wrong? It's wrong because the regression estimates the expected value of the log of y. It does because the log of y is your dependent variable. But the expected value of the log of y is not equal to the log of the expected value of y. Why is this true? Why are these two not equal? They're not equal because the expected value is a linear operator and the log is not linear, and so you can't do this. You can't swap the log function and the exponentiation function. And so the exponentiation of the expected value of the log of y, which is the dependent variable, is not equal to y. It doesn't work. With simulation it works, but it doesn't work this way. More generally, it is just not true for some nonlinear function g, and it is therefore not true in general, that the expected value of g of y is equal to the g of the expected value of y. It's just not true, unless g is linear. Okay. Another important step is we're using simulation, so we're approximating things. So whatever your quantity of interest is, whatever your estimate of that quantity of interest is, it's an approximation. It's going to be a number, and that number is approximated. The error in approximation is a function of how many simulations you've used. Did you use enough simulations? We can actually figure that out. It's not that hard, right? So what you do is just run the algorithm twice, look at how many digits of precision you get, right? If you have a 4-digit number, 0.1234, let's say, and you run it again and you get 1279, and you run it again and you get 1211, then it's precise up to 2 digits. So if you're willing to only present 2 digits, no problem, you're done. If you need to present 4 digits for the substantive problem at hand, then increase the number of simulations, m, and just rerun the whole thing. No big deal, okay? But you need to make sure to do this step. Otherwise, you could be presenting results that have approximation error in it for no good reason. Okay, so we sort of always do that. There's lots of ways of increasing speed. The calculations we're doing for simple models is easy and not too big a deal. For more complicated models, it might actually take a long time. If it's fast, no problem. If it's slow, we're going to have to do something. So what do? First time, every time, just ignore all the tricks. Just see whether you can get a result. If it takes too long, then of course you're going to have to pay attention to these tricks, to different ways of doing things, to more interesting or more difficult ways of approximating the simulation functions. And if we do that, then we'll be able to speed things up. So I'm not going to tell you what those are because they depend upon the particular model, and we will work on those things as they come up. But it's important that you just understand that if you get stuck because something's really slow, well, odds are you probably have a coding bug, because that's the most likely explanation of almost anything we do. But if not that, it could be the case that there are faster ways of doing some of these things. And as long as you carry away that knowledge, then you'll know to ask when you run into that situation at some point. Okay. This is easily done in Clarify for Stata or Zelig in R. And but you can do it, and you will be doing it yourself. So it's important to understand how it works regardless of how we do it. Okay, so I'm going to do 2 replications to give us a feel for how this works. You can follow along in the paper we wrote. As I said, I wrote the paper out of this class and the class out of the paper. So this is King, Tomz, and Wittenberg again. I'm going to replicate an analysis in a book by Steve Rosenstone and Mark Hansen. Great book, great analysis. They run a logit to try to explain voter turnout. And their explanatory variables are age squared, education, and income, and race. And what Mike Tomz and Jason Wittenberg and I tried to do was to come up with some knowledge that Mark and Steve in their book didn't express, didn't include, but we could find without changing any assumptions in their original analysis. Okay, so that was our trick, that by presenting results better, we sought to be able to find knowledge in their results that they didn't find, but without making any different assumptions at all, without analyzing the data differently, without making any methodological corrections at all. We assumed the same things that they assumed, and we just tried to extract more knowledge. Okay, so we identify one interesting quantity of interest, which is the effective age on the probability of voting, that is turnout, given income and race, but not given education, because we want to include education in there. So we use 1,000 simulations, and we compute a 99% confidence interval. And this is the way we presented our results, and these results were in our paper. They weren't in Rosenstone and Hansen's book, but they enhance their original results. So let me now explain this figure, because it conveys something of some interest, I think, substantively. So in the horizontal, and the key thing here is you don't have to know any statistics to understand this. So the horizontal axis is the age of the respondent. So it's going 18 up to 95 here, right? The age of the respondent. The vertical axis is the probability of voting, which goes from 0.2 up to 1, just as we have the number here. We have a line here for high school degree, people with a high school degree, and a line here for a college degree. And the vertical bars for each point represent a 99% confidence interval. Okay, so this is I'm going to explain how to calculate this thing, but substantively, what does this mean? This means that the probability of voting is higher the older you are, until you get to very old ages, in which case it becomes very uncertain, because there's probably many fewer people in the sample who are 90 or 95 years old. Having a college degree means you're much more likely to vote than if you only hold a high school degree. But either degree means, having either degree, you have a higher probability of voting the older you get. Okay. Now, to me, this is interesting and substantive, and as it happens, it's a sort of cool graphic. I know it was taken as a cool graphic because in the first probably 5 years after the article was published, I received probably 200 emails asking for the code to produce this graph, because lots of people thought that was an interesting way to produce a graph. And I thought there were lots of other interesting graphs in the paper, but for some reason this one really resonated with people. And the fact that it resonated with people was really useful for me to know. I'll also mention that about 15 years after our paper was published in 2000, and I'd been teaching this graph for a long time, and lots of people, of course, have read the paper, and all those people had requested code for it. And this Clarify is very, very widely used, and it's taught in lots and lots of classes. It's a standard way of presenting results now in a lot of ways. Something like 15 years after we presented the paper, an undergraduate in this class raises his hand and says, "Hey, this is interesting. Look at all this. How is it that you have 18-year-olds who graduated from college? How do you get estimates for 18-year-olds who graduated from college?" So that was really an excellent point. Like, we didn't notice this. No, our reviewers in the article didn't notice this. Apparently none of the readers of the article noticed this. Nobody in this class had noticed it before, but this one undergraduate noticed something. Okay, so what does that mean? What is it that he noticed? He noticed a really interesting point. The interesting point is that you can stick anything into the model for a value of X, even if it doesn't make any sense, right? And the model can just dutifully make a calculation. You could stick into that model a 3 and it would produce a prediction, right? It wouldn't be a very interesting prediction, of course. In fact, you can put in a number -12, it wouldn't make any sense. And probably allowing college degree people who are 18 years old to have predicted values from a model which is calculated or estimated based on data with probably nobody in the data set. I haven't checked, but almost nobody certainly in the data set who could be described that way is probably the wrong thing. In fact, what is the voter turnout of the very specialized group of 18-year-olds who get a college degree? I mean, I don't know, but extrapolating that number from 24-year-olds and 72-year-olds who have college degrees and high school degrees doesn't seem like a good idea. Okay, so there's lots of important things in that result. Okay, so how do you calculate? How do we simulate in order to get this figure? So let's take one example. Let's take age 24, which is down over here on the graph. And we have education equal high school. So that means we're going to be calculating this number over here somewhere. What do we do with income? So we're going to choose to use the average value. And race, we're going to choose the modal value, which is white. Those are not the correct numbers. Those are just the numbers we chose. I could criticize those. For example, we chose the average value. Well, the average value of income, it actually goes up by age, right? And we held it constant. So maybe it would have been better to use the average value of income for 24-year-olds and then choose the average value of income for 30-year-olds and then the average value of income for 36-year-olds. The only difficulty with doing that is if we did that, then we would be looking at the effect not only of age on the horizontal axis, but also income. So maybe we don't want to do that. But income does go up with age, so maybe it is only realistic to do that. There's no correct answer to this question, but it is something that you have to consider when you run these models. None of these are automatic questions. Similarly, just choosing race equal white and ignoring minorities is not the right answer. But almost all the people in the sample were actually white. You know, it was a representative sample, so I don't know the numbers off the top of my head, but probably 20% were minorities or something like that. So we could also present the whole thing for minorities. We could present it for a mixed combination or something like that. Whatever you choose has implications, and it's very important that we pay attention to those implications. Okay. So we set the values of C. We choose X sub C. Then we run our logistic regression. We simulate 1,000 betas, beta tildes, indicating they're simulated. We take the beta tildes, stick them into the systematic component. In this case, it was a logit. So we stick it into 1 over 1 plus e to the minus x beta tilde, because we got the estimation uncertainty for beta tilde. We put them in here. We now have the eta tildes there. By the way, eta tilde here is pi in other notes, but for whatever reason we used eta here. Notation is not going to be consistent across all of methodology. It's not usually consistent within any one article, although it often is. So you have to get used to that and understand what it is that people are going after. So you sort these simulations of this one quantity in numerical order, and we choose to get the 99th confidence interval, we choose the 5th and 995th values, and that gives us the vertical bar that is over here that we plotted for 24-year-olds. Okay, so that gives us that. From that we plot the vertical line at 24, and so that's the confidence interval. We then repeat exactly the same procedure for every other age for a high school degree, and then for every other age for college degree, and that's exactly how we got this graph. And that was the whole thing. Okay, let me do one more replication, and then we'll finish. So this is a replication of Jeff Garrett's really interesting article, and what he was interested in was predicting government spending as a percent of GDP. So how much do governments spend, basically? And what his key causal variable was, the thing that he really cared about showing had an effect on government spending, was left labor power. And high is a solid line and low is a dashed line in these graphs. Garrett reported the 8-point estimates in these graphs. So let me explain what the graphs are, because what we did is we took the 8-point estimates and made them distributions. So at the top here, we have, let's change to our other little gizmo here. This is low exposure to trade, high exposure to trade, low capital mobility, high capital mobility. And so the horizontal axis of each of these is government spending as a percent of GDP, all 4 of those. And the vertical axis is just the density. So we now have a dashed line for the distribution of government spending for low left labor power, and a solid line for high left labor power. So for countries with high capital mobility, there's a big difference between these two. The government spending as a percent of GDP went from 42 to 40 to maybe 45%, that's a big it's a big difference. But for low capital mobility, there's a big overlap in the two. Similarly, for high exposure to trade, there's a big difference between government spending. The effect is about the same here, even though it's a little more uncertain than down here. There's a clear separation between the two histograms of simulated values. Over here, for low exposure to trade, there wasn't much of a difference. So what Jeff Garrett did is he looked just at the 8-point estimates, right? 2, 4, 6, 8, just at the 8-point estimates, and he said, hey, the left labor power is always to the high left labor power is always to the left of, is always to the right. That is higher government spending than low left labor power. And he concluded that's really interesting. And it is absolutely interesting. However, when there's low exposure to trade or low capital mobility, even though the point estimate, perhaps the expected value is to the right, there's too much uncertainty to really distinguish the two. And so we think that this was a great article. Garrett did a great job, found lots of interesting things, but we could add some more value by simulating. And in this case, by representing the uncertainty along with the point estimates. And the uncertainty here shows that when there's high exposure to trade or high capital mobility, his point comes through loud and clear, but when there's low exposure to trade or low capital mobility, the effects are very small and probably not really distinguishable from zero. So that's the new information that I think that we would learn from this. And one question that I would leave for you, where is it, is how could we summarize this with less real estate? Because after all, the only thing he had were 8 numbers. Now we had more than 8 numbers. We had maybe the 8 numbers plus the 8 uncertainties. But still, we took this entire graph to represent it. And when do you do that, right? When do you do that? That's an important thing to pay attention to. When do you put things in a graph? So we'll talk about this, but the relevant thing is not to convey to people that you did the analysis, okay? So in class papers, it's very common that you make your results a table or a figure to show the instructor that you did the analysis. That is not what you want to do when you're writing a professional paper. When you're writing a professional paper, your figures and tables, people focus on those. That's like a a highlight, right? It's a big asterisk in the middle of your paper. No one's going to read your whole paper, and you somehow have to get them to pay attention, to get the readers to pay attention to the important points. So the title matters a lot. The abstract matters a whole heck of a lot. The introduction really matters, right? One paragraph on some page that I don't remember, it doesn't matter that much. The section headings matter, but the table and figures matter a lot. And so what goes in those table and figures is what it is you want to convey to your readers. That's the important thing. So even though there's only 8 numbers with 8 uncertainties, if this is a central important point in your paper, you present this to your readers. If it's not that, that's central, then don't put it in a figure. Okay. So the things that go in the figure are the things that where you want to make a real important point. Okay. All right. So that's interpreting, understanding, and presenting statistical results. We will, of course, do this again and again in the context of lots of different statistical models, about which more soon. So I'll see you next time. Thanks.